Hey there and welcome. This is the third and final part of our basic series going over the fundamentals of computing. I am going to break this into two videos. This is the first part, Part A, of our look into programming. If you haven't yet watched the previous videos in the series, click on the link above to watch my first on binary and hex, and follow along from there. In this episode, we're going to delve into the programming basics. We're going to use our previous knowledge to understand just how programs work, what they do, and what they can be used for. As always, I recommend grabbing a pencil and paper for notes and diagrams, or if you use any note-taking software, to use that. So how do we program? How can we make a program work? Programming, in its most literal sense, is giving commands to computers, giving them a problem to solve, or giving input and expecting output. Programs can be anything from the web browser you're watching this on to a AAA game title and everything in between. We're going to look at programming as a whole in a language agnostic way. What do I mean by this? Well, as you are probably aware, there are many languages developed over the past 80 years in order to interact with computers, and it would be almost impossible to describe them all in a video. So, we're going to look at the basic rules and concepts that most languages follow, to get a basic understanding of them. So let's begin. First up, we will look at variables and data types. Variables are basically storage for values. Think of them like a box. In some languages, you can have one box that can have any type of variable inside, and for others, specific boxes for specific types. When I say types, this can be numbers, letters or symbols, or Boolean values. Let's look at our first type, numbers. When we store numbers in code, they come in two flavors, whole numbers, or decimalized/fractional numbers, like pi. Focusing on whole numbers for now, we can store values in various sizes. A number can, depending on whether it is signed or unsigned, store different size values. Bringing it back to binary for a moment. For a byte, we can count up to 255. This would be an example of an unsigned number. Now, for signed numbers, we can reserve the 8th bit, the 128 place, and use that to denote whether a number is negative or positive, letting us count from negative 128 up to 127. And this is seen in our first number variable, coincidentally called a byte. As we can see, we have signed and unsigned variants of a byte, and how it could be coded using pseudocode and its bit width. Bit width, like explained in the first video, is how many bits it has. It's the range of bits it encompasses. So, for the byte, we can, depending on whether it's signed or unsigned, store values of either negative 128 to 127, or 0 to 255. And this is using a bit width of 8 bits or 1 byte. After byte, we have the short type. As shown, a short can either be negative 32,768 to 32,767, or 0 to 65,535, and uses a bit width of 16 bits or 2 bytes. Moving on, we have the int, short for integer type. Here, we can see the int type can store values of either negative 2.14 billion to 2.14 billion, or 0 to 4.29 billion. This uses a bit width of 32 bits or 4 bytes. And finally, we have the long type. This can store massive numbers. Not great for me right now having to say them, but anyways, the long type can store values of either negative 9.22 quintillion to 9.22 quintillion, or 0 to 18.44 quintillion. All this fits into a bit width of 64 bits, or 8 bytes. Now we've looked at whole numbers, let's tackle decimalised numbers. Like mentioned earlier, decimalised numbers are fractional numbers like pi. These are represented by two different types, a float and a double. A float is short for floating point, and floating point means the decimal point. These numbers have insanely massive ranges, and have the same range regardless of whether it is a positive or negative number. We represent these numbers in scientific notation just due to their size, but I shall show the real numbers too. As we can see, the maximum is a whole number, 340.2 undecillion, or 3.402.823.466.385.2886 times 10 to the power of 38. I think my tongue needs a rest after that. But we have two minimums. One is a normal minimum, the other a subnormal minimum. The normal minimum is the minimum full precision value. A float in this case can store this, or 1.175494350.822.2875 times 10 to the power of negative 38. The subnormal minimum is the smallest number possible able to be stored in the float. We lose precision in this range due to a bit being used to denote that we are in this range. This number is, or 1.401298464324.81707 times 10 to the power of negative 45. So what's the difference? Why two minimums? Well, sometimes you need to measure or use extremely small numbers, so we can technically go down to those numbers. Let's view it in this way. We have full precision in our float from the max to the normal minimum. We have less precision from our normal minimum to our subnormal minimum. And anything below our subnormal minimum, well, that's too small to count and underflows to 0. Finally, we can see that the float has a bit width of 32 bits or 4 bytes. Now, let's look at our last number, the double. A double means double precision, and it is doubly precise compared to a float, having a bit width of 64 bits or 8 bytes. For the double's maximum, we have this number, or 1.797693134.862.3157 times 10 to the power of 308. For the double's normal minimum, we have this, or 2.225.073.858.507.2014 times 10 to the power of negative 308. And finally, for the double's subnormal minimum, we have this, or 4.9406564584124654 times 10 to the power of negative 324. With the double done, that is the end of our number types. Let's focus on text or character types now. First up, we have the character type, sometimes seen as char. This can store a single Unicode symbol. It has a bit width of 8 bits or 1 byte for UTF-8, 16 bits or 2 bytes if it uses UTF-16, or up to 32 bits or 4 bytes for full Unicode. The last text-based type is string, essentially a group of characters. So, its bit width is dependent on how many characters we have. This means it would be n times whatever our character format is, so the formula would be character count times format bit width. With that done, let's look at our last main type, Booleans. Booleans are named after George Boole, the creator of Boolean algebra, which deals with true, false, and logical operations like and, or, not, etc., like our logic gates. In programming, Booleans hold either a true or a false value. They have a bit width of 1 bit or 0.125 bytes. In other words, an eighth of a byte, not even a mouthful. But in actuality and for simplicity, they are stored in memory as 8 bits or 1 byte. That's it for data types. Thanks for following along, and click above to watch the next episode in the series where we look at operators and control flow. But give it all a go yourself. I recommend downloading Visual Studio Code. It's on all platforms and packed with features. Try it out yourself at code.visualstudio.com. And as always, if you have any questions, feel free to reach out at fluffies.bytes@gmail.com. I'd love to hear from you. But for now, have fun, and I'll see you in the next video.